Hello there, and welcome to the Sleeping Physicist. If you are someone who enjoys unwinding by thinking about particles, gluons, and the quiet structure underlying the universe, you are in the right place. Here, we let our attention settle into real physics and real discoveries, taken slowly and carefully as we explore the full shape of what we currently understand about this topic. Some ideas may feel surprising at first, but everything you hear is grounded in what experiments and theory have patiently revealed about nature. And if you find yourself enjoying these unhurried explorations, you are welcome to like and subscribe. For now, allow yourself to settle in. Let the day loosen its hold. Let curiosity take the lead. And let us begin. What are gluons, and how do they create the force that binds the very core of matter together? If we begin anywhere, we begin with the simple fact that matter holds together. An atom has a dense center called the nucleus. Inside that nucleus are protons and neutrons packed tightly together. Protons carry positive electric charge. Electric charges of the same sign repel one another. If only electromagnetism were at work, the positively charged protons would push apart violently. The nucleus would not remain intact. Yet nuclei are stable. Many of them persist for billions of years. That stability tells us that another force must be present. It must be stronger than electric repulsion at extremely small distances. It must act over distances comparable to the size of the nucleus. And it must operate in a way that allows protons and neutrons to remain bound without flying apart. This force came to be known as the strong interaction. At first, it was understood only as a property of protons and neutrons themselves. The nucleus was treated as a cluster of these particles held together by a short-range attraction. This description worked well for many practical calculations. It explained patterns of nuclear stability. It allowed predictions about radioactive decay. It gave structure to nuclear physics. But the deeper question remained: what binds the protons and neutrons internally? As experiments improved, physicists learned that protons and neutrons are not indivisible objects. They contain smaller constituents. When high-energy electrons were scattered off protons, the results showed that something inside was absorbing momentum in concentrated points. The proton behaved as if it contained compact internal components. Those components came to be called quarks. Quarks carry fractional electric charge. They combine in specific ways to form protons and neutrons. A proton contains 3 quarks. A neutron contains 3 quarks as well, arranged slightly differently. Now the puzzle shifts inward. If protons are made of quarks, then what binds the quarks together? The attraction must be extraordinarily powerful. It must overcome not only electromagnetic repulsion between quarks of like electric charge, but also the natural tendency of energetic particles to separate. It must be strong enough to confine quarks permanently inside composite particles. This deeper layer of binding is the true domain of gluons. Gluons are the carriers of the strong interaction at the level of quarks. They are not secondary details. They are the mechanism by which the force operates. Without gluons, quarks would not form stable structures. Without stable quark structures, there would be no protons. Without protons, atoms as we know them would not exist. So, before we speak about their properties, it is helpful to recognize their necessity. The stability of matter implies a force. The internal structure of protons implies a deeper force still. Gluons arise as the carriers of that deeper binding. They are the agents of cohesion at the smallest accessible scale of ordinary matter, and that is where our careful exploration begins. Once quarks were identified as the internal constituents of protons and neutrons, the picture of the nucleus changed in a quiet but fundamental way. The strong interaction was no longer only a force between protons and neutrons, it had to be something deeper, acting directly between quarks themselves. Protons and neutrons became structured objects, not elementary ones. Their stability depended on dynamics unfolding at a smaller scale. Experiments in the late 20th century made this internal structure visible in an indirect but convincing way. When electrons were accelerated to extremely high energies and directed toward protons, they did not scatter as though striking a smooth object. Instead, they scattered as if they were hitting compact, point-like targets inside. The patterns of deflection revealed that momentum was being carried by smaller constituents. These constituents behaved almost like free particles when probed at very short distances. That observation was unexpected. If the force between quarks were always extremely strong, they would not appear nearly free under such scrutiny. Something subtle was happening. At this stage, physicists faced two simultaneous requirements. First, quarks had to be bound tightly enough that they never escape the proton. No isolated quark had ever been observed in any experiment. Every attempt to separate one resulted instead in the production of a new composite particles. Second, at very short distances inside the proton, quarks had to behave as though the force between them weakened. These two features appear contradictory at first glance. A force that prevents separation entirely would seem to be strongest at all distances, yet the data suggested otherwise. The resolution required a new kind of force law, one unlike gravity or electromagnetism. In gravity, attraction weakens with distance. In electromagnetism, electric forces also diminish as objects move apart. Both forces become stronger as particles approach one another. The strong interaction, as experiments suggested, behaves in a reversed manner. At very short distances it weakens, at larger separations it strengthens. This unusual behavior is not arbitrary. It arises from the internal structure of the field that mediates the interaction. Whatever carries the strong force must interact in a way that changes the strength of the force depending on distance. That carrier is the gluon. Before we describe gluons directly, one more structural feature must be introduced. Quarks come in different varieties, not only in terms of mass and electric charge, but also in a distinct type of charge that governs the strong interaction. This charge is not electric. It is a new property altogether, and it is this property that gluons respond to. Understanding that new charge is the next step toward understanding gluons themselves, and so the focus narrows further, from nuclei to protons, from protons to quarks, and now from quarks to the property that allows them to bind. That property is called color. To understand gluons, we must understand the charge they respond to. In electromagnetism, electric charge comes in two kinds, positive and negative. Opposites attract, like charges repel. The structure is simple and symmetric. The strong interaction requires something more intricate. When physicists examined how quarks combine inside protons and neutrons, they discovered that three quarks could occupy the same quantum state without violating the rules of quantum mechanics. According to those rules, identical particles cannot share identical states unless an additional distinguishing feature exists. Something had to differentiate the quarks beyond their mass and electric charge. That additional feature became known as color. Color charge comes in three varieties. By convention, they are called red, green, and blue. These names are labels only. They do not refer to visible light or optical color. They are placeholders for three mathematically distinct types of strong charge. The important point is not the names, but the number. There are three independent types of this charge. Quarks each carry 1 unit of color charge. A proton contains 3 quarks, and each carries a different color. When red, green, and blue are combined in the correct way, the total state becomes color neutral. The combination does not display net color to the outside world. This neutrality is essential. Only color-neutral combinations appear as isolated particles in nature. Protons are color-neutral. Neutrons are color-neutral. Mesons, which are made of a quark and an antiquark, are also color-neutral because the color of the quark is balanced by the corresponding anticolor of the antiquark. Color neutrality plays a role similar to electric neutrality in atoms. An atom with equal positive and negative charge does not exert a large electric force at long distances. In a similar way, a color-neutral particle does not exhibit the full strong force beyond a very short range. But there is a key difference. Electric charge is carried only by matter particles like electrons and protons. The photon, which transmits the electromagnetic force, carries no electric charge itself. It does not interact directly with other photons in ordinary circumstances. Gluons are different. Gluons carry color charge. More precisely, each gluon carries a combination of color and anticolor. Because of this, gluons can interact not only with quarks but also with other gluons. The field that mediates the strong force is therefore self-interacting. This feature changes everything about how the force behaves. Instead of spreading outward smoothly and weakening with distance, the strong field organizes itself in a more constrained and structured way. The interactions between gluons reshape the field lines themselves. The existence of 3 colors also determines how many distinct gluons are possible. The combinations of color and anticolor are not arbitrary. They are governed by the internal symmetry of the theory. When the structure is worked out carefully, it leads to 8 independent gluon types. Each type corresponds to a particular way of carrying color between quarks. The names and mathematical details are secondary to the structure. Quarks carry color. Gluons carry color and anticolor. Color must balance in observable particles. And because gluons themselves carry color, the strong force interacts with itself. This self-interaction is the key that explains why quarks are never seen alone. We can now turn directly to gluons as physical entities and examine how their behavior shapes the force they transmit. Now that color charge is in view, we can look more directly at the particle that carries the strong force. In modern physics, forces are not treated as invisible pulls acting across empty space. Instead, they are understood as interactions between fields. Every fundamental force corresponds to a field that fills space. Particles are excitations of those fields. When 2 particles interact, they do so by exchanging small packets of the field. In electromagnetism, that packet is the photon. In the strong interaction, that packet is the gluon. A gluon is the quantum of the strong field. It is the smallest transferable unit of that interaction. When one quark influences another, what actually occurs is an exchange of gluons between them. But this exchange is not like throwing a ball from one place to another. It is better imagined as a continuous adjustment of a shared field. The gluon represents a localized ripple within that field, carrying color charge from one quark to the next. When a quark emits or absorbs a gluon, its color changes. A quark that was labeled red may become green after emitting a red anti-green gluon. The total color of the system remains balanced, but the internal arrangement shifts. This continual exchange never stops. Inside a proton, quarks are not static objects sitting in fixed positions. They are dynamic participants in an ongoing interaction. Gluons are constantly being exchanged, reabsorbed, and interacting with one another. Because gluons themselves carry color charge, they can emit and absorb other gluons. This creates a network of interactions rather than a simple pairwise exchange. The strong field becomes self-coupled. That self-coupling is what gives the strong force its unusual character. It prevents the field from spreading freely outward. It encourages the field to organize itself into narrow structures between quarks. The gluon is therefore not merely a messenger. It is an active participant in shaping the behavior of the force. With this picture in mind, we can begin to understand why quarks remain confined within composite particles. And that confinement is the next idea we will examine carefully. To understand confinement, it helps to compare the strong force with something more familiar. Consider two electrically charged particles. If you pull them apart, the electric force between them weakens. The field spreads outward in all directions. Its influence becomes diluted with distance. This is why the pull between two charges fades as they separate. The strong force does not behave that way. When two quarks are close together, the gluon field between them is relatively weak. At extremely short distances, quarks move almost as though they are free. This behavior has been measured directly in high-energy scattering experiments. The closer the quarks are forced together, the less tightly they seem to interact. But when quarks are pulled apart, something very different happens. Instead of spreading outward, the gluon field gathers into a narrow tube connecting the quarks. The energy does not disperse into space. It remains concentrated between them. As the distance increases, the energy stored in this tube increases steadily. An ordinary elastic band offers a gentle analogy. When it is relaxed, it exerts little force. As it stretches, tension grows. The farther it is pulled, the stronger the restoring force becomes. The gluon field behaves in a structurally similar way, though the underlying physics is more subtle. The energy between quarks grows roughly in proportion to their separation. The system resists being pulled apart. Eventually, if enough energy is supplied, the field does not snap in the usual sense. Instead, it becomes energetically favorable to create a new quark and antiquark pair from that stored energy. The original quarks do not emerge alone. They reorganize into two color-neutral particles. This process has been observed repeatedly in particle collisions. Attempts to isolate a single quark always produce sprays of new particles instead. The phenomenon is consistent and universal. This is confinement. Quarks and gluons are never seen in isolation under ordinary conditions. They exist only inside color-neutral combinations. The strong force does not allow its carriers to wander freely, and this property follows directly from the self-interacting nature of gluons. The idea that quarks can never be isolated might seem restrictive, but it carries a deeper implication about how the strong force behaves at very small scales. Earlier, we noted something that at first felt contradictory. When quarks are pushed extremely close together, the force between them becomes weaker. When they are pulled apart, the force becomes stronger. This reversal is not an approximation. It is a measured property of the theory. This behavior is called asymptotic freedom. The phrase means that as the distance between quarks approaches zero, their interaction approaches freedom. They still interact, but more gently. In high-energy experiments, where particles are probed at very short distances, quarks behave almost like independent entities inside the proton. This discovery was one of the great insights of 20th century physics. It explained why early scattering experiments saw quarks acting nearly free. The strong force does not trap quarks tightly at short range. Instead, it allows them room to move when compressed together. The reason lies again in the gluons. Because gluons carry color charge, they interact with one another. At short distances, the cloud of virtual gluons surrounding a quark rearranges itself in a way that partially shields the color charge. the effective interaction becomes weaker. At larger distances, that shielding effect diminishes. The gluon field lines reinforce rather than dilute. The interaction strengthens and confinement emerges. So the same property that prevents quarks from escaping also allows them limited freedom at extremely small separations. There is a quiet consistency in this structure. Close together, quarks behave almost freely. Far apart, they are tightly bound. Both behaviors arise from the self-coupled nature of the gluon field. This dual character defines the strong interaction across all accessible scales. The unusual behavior of the strong force was not accepted simply because it was mathematically elegant. It was tested. One of the clearest confirmations came from experiments in which electrons and positrons were accelerated toward one another and allowed to collide. When they meet at high energy, they can transform into a quark and an anti-quark. Those newly created quarks then rush away from one another. If quarks could exist freely, detectors would record just 2 outgoing particles. But that is not what is seen. Instead, each quark produces a narrow spray of new particles. These sprays are called jets. They form because as a quark attempts to separate, the gluon field between it and its partner stretches and stores energy. That energy converts into additional quark and anti-quark pairs. Those pairs then form color-neutral particles that move outward in roughly the same direction as the original quark. The result is not a single particle, but a structured cascade. In many events, 2 jets appear, consistent with a quark and an anti-quark moving apart. But sometimes a third jet is visible. This third jet corresponds to the emission of a gluon from one of the quarks, before confinement reshapes everything into observable particles. The pattern of these 3 jet events matches precise theoretical predictions derived from quantum chromodynamics. The angles between jets, the distribution of energy, and the frequency of such events all agree with calculations that include gluons as real physical carriers of the strong interaction. Through these experiments, gluons moved from theoretical necessity to empirical reality. They are not speculative elements of an abstract model. Their influence leaves measurable signatures in high-energy collisions. Jets in particle detectors are the visible traces of invisible gluon exchanges, and through those traces, the structure of the strong force becomes experimentally grounded. Those jets reveal something else that is less immediately visible, but equally important. When the energy of a collision is carefully analyzed, it becomes clear that a large fraction of a proton's internal motion is not carried by quarks alone. Inside a proton, quarks are only part of the story. They account for some of its measurable properties, but not all. When experiments measure how the proton's momentum is distributed among its internal constituents, the result is surprising. Gluons carry a substantial share of that momentum. This is striking because gluons are massless in the underlying theory. They have no rest mass in the way quarks do, yet they contribute significantly to the proton's energy. And through the equivalence of mass and energy, that energy contributes directly to the proton's mass. If one were to add together the intrinsic masses of the 3 quarks inside a proton, the total would account for only a small portion of the proton's measured mass. The majority arises from the energy stored in the dynamic gluon field and in the motion of quarks confined within it. The proton is therefore not a simple container holding 3 solid objects. It is a dynamic system in constant internal activity. Quarks exchange gluons continuously. Gluons split into quark and antiquark pairs and recombine. Virtual excitations appear and vanish within the constraints allowed by quantum mechanics. The mass of ordinary matter is largely the energy of confinement. This realization changes how we think about substance. What feels solid and weighty in the everyday world is not primarily the mass of elementary constituents. It is the energy bound up in fields, particularly the gluon field that prevents quarks from separating. The stability of matter and its mass both trace back to the same source, the structured self-interacting field carried by gluons. If most of the proton's mass arises from energy stored in gluon fields, then the vacuum surrounding those fields cannot be entirely empty. In everyday language, a vacuum suggests absence. In quantum field theory, it means something more subtle. The vacuum is the lowest energy state of a field, but it is not a featureless void. Even in that lowest state, fluctuations are present. Fields are never perfectly still. For the gluon field, this restless character is especially important. Because gluons interact with one another, the vacuum of the strong interaction has structure. The field does not simply vanish when no quarks are nearby. Instead, it maintains a background configuration shaped by self-interaction. These configurations influence how quarks behave when they appear. One way to sense this is through the idea of vacuum polarization. Around any quark, the gluon field rearranges itself. Virtual gluons and quark pairs briefly emerge and dissolve, subtly modifying the effective strength of the interaction. This constant rearrangement is part of why the strong force changes with distance. The vacuum therefore participates in confinement. It is not merely a passive stage on which quarks move. It contributes to the way flux tubes form between quarks. It influences how energy accumulates as separation grows. Computational studies of quantum chromodynamics, especially those performed on discrete space-time lattices, reveal that the vacuum contains patterns that help sustain confinement. These studies do not rely on speculation. They use the fundamental equations of the theory, translated into numerical form, and solve them through large-scale computation. The results reproduce observed particle masses and interaction strengths with impressive accuracy. This agreement reinforces a central conclusion. Gluons are not isolated messengers. They are part of a deeply interconnected field whose structure extends even into what we call empty space. Although quarks and gluons are permanently confined under ordinary conditions, there are environments where that confinement can loosen. If matter is heated to extraordinary temperatures, far beyond anything encountered naturally on Earth, protons and neutrons no longer remain intact. The energy becomes so intense that the boundaries between individual hadrons dissolve. Quarks and gluons are no longer restricted to single protons or neutrons. They move within a larger shared region. This state is known as quark-gluon plasma. It is not a gas of free quarks drifting independently. Confinement is reduced, but the strong interaction remains active. The particles still interact strongly with one another. What changes is the scale over which they are confined. Such conditions existed naturally in the early universe, a fraction of a second after the Big Bang. At that time, temperatures were so high that matter could not settle into stable protons and neutrons. As the universe expanded and cooled, confinement reasserted itself. Quarks and gluons combined into the composite particles that later formed atomic nuclei. Today, quark-gluon plasma can be created briefly in heavy ion collisions. Large nuclei are accelerated to near the speed of light and brought into collision. For an instant, temperatures comparable to those of the early universe are reached. Detectors observe the resulting spray of particles and infer the properties of the plasma phase. One surprising result is that this plasma behaves less like a thin gas and more like a nearly perfect fluid. Its internal friction appears extremely low. The gluon field, even in this deconfined state, maintains strong collective behavior. These experiments show that confinement is not an absolute rule without exception. It is a property that depends on temperature and density. Under ordinary conditions, gluons bind quarks tightly into color-neutral particles. Under extreme conditions, that binding reorganizes into a new collective phase. The strong interaction remains present throughout. Its form changes, but its governing structure persists. The existence of quark-gluon plasma also clarifies something about the strength of the gluon field itself. Even when confinement relaxes at extreme temperature, the interaction does not disappear. The plasma remains strongly coupled. Quarks and gluons continue to influence one another through dense, collective motion. This reinforces a central idea. The strong force is not strong merely because it binds tightly at large distance. It is strong because the gluon field is deeply self-connected. Its carriers influence one another continuously. That mutual interaction gives the field resilience across changing conditions. To understand why the theory takes this specific form, we need to consider a principle that guides all modern descriptions of forces. In physics, symmetries are not decorative features, they are organizing rules. A symmetry states that certain transformations can be performed without changing the fundamental laws. When such a symmetry is imposed locally, meaning independently at every point in space and time, new fields must appear to preserve consistency. In electromagnetism, requiring local symmetry leads to the electromagnetic field and the photon. For the strong interaction, a more intricate symmetry is required. The symmetry reflects the existence of three types of color charge. Demanding that the laws remain consistent under local changes in how color is defined forces the introduction of a field with specific properties. That field is the gluon field. Its self-interaction is not optional. It arises directly from the symmetry structure. Because the symmetry is based on three color charges interacting in a particular way, the resulting field necessarily contains 8 independent gluon types. Each corresponds to a specific way. Color can be exchanged while preserving the underlying symmetry. The structure of quantum chromodynamics is therefore not arbitrary. It is tightly constrained. Once color symmetry is chosen, the existence and behavior of gluons follow with little freedom to adjust them. The theory's unusual features are consequences of that internal consistency. Because the structure of the strong interaction is fixed by symmetry, its predictions are precise. Yet precision in principle does not always mean simplicity in practice. At very short distances, where the interaction becomes weak, calculations can be performed using systematic approximations. Physicists expand the interaction step by step and compute measurable quantities such as scattering probabilities. These predictions have been tested in high-energy experiments and match observation with impressive accuracy. At larger distances, however, where confinement dominates, the interaction becomes too strong for those same approximations to work. The gluon field does not allow a simple expansion. Its self-interaction ties together fluctuations across scales. To study this regime, a different method is required. One powerful approach is called lattice quantum chromodynamics. In this method, space and time are represented as a discrete grid. The equations governing quarks and gluons are translated into numerical form on that grid. Supercomputers then evaluate how the fields behave. This approach does not simplify the theory. It retains the full structure of gluon self-interaction. What it changes is the method of solution. The results are remarkable. Lattice calculations reproduce the measured masses of protons and neutrons with high precision. They predict how quarks arrange themselves inside hadrons. They confirm that confinement arises naturally from the theory without additional assumptions. These successes strengthen confidence in the underlying framework. The strong interaction, though mathematically demanding, remains internally consistent across all accessible scales. The same gluon field that explains jet patterns in particle collisions also explains the mass of the proton when computed from first principles. Different tools are needed at different distances, but the governing structure does not change. When the equations of quantum chromodynamics are solved numerically, another insight becomes clear. The proton is not simply three quarks exchanging gluons in an otherwise empty interior. It is a seething system of activity in which gluons themselves can briefly transform. Because energy and mass are interchangeable, a gluon with sufficient energy can momentarily produce a quark and an anti-quark pair. These pairs are not permanent additions to the proton structure. They appear and vanish within the constraints allowed, yet while they exist, they contribute to the internal dynamics. This means the proton contains more than its three so-called valence quarks. It contains a fluctuating sea of additional quark pairs and gluons. The gluon field is responsible not only for binding the primary quarks, but also for sustaining this constantly shifting background. Measurements of how momentum is shared inside the proton confirm this picture. At high energies, experiments reveal that gluons can carry even more of the proton's momentum than the valence quarks do. The internal motion is dominated by the gluon field. The proton therefore becomes less like a small solid sphere and more like a dynamic region of confined energy. Its identity is defined by a stable pattern of interactions rather than by static components. Even so, certain properties remain sharply defined. The proton has a fixed electric charge, it has a specific mass, it has a well-measured spin. These stable characteristics arise from the collective behavior of quarks and gluons bound together in a precise configuration. The complexity inside does not produce ambiguity outside. The structure is intricate, but its observable features are stable. In this way, gluons provide both motion and order. They generate continuous fluctuation, yet they also enforce the confinement that preserves identity. The stable identity of the proton, emerging from such internal motion, points toward a broader consequence of gluon dynamics. If the mass of ordinary matter arises largely from confined energy, then the visible weight of the world is mostly a manifestation of the strong interaction. The up and down quarks inside protons and neutrons have relatively small intrinsic masses. On their own, they would account for only a small fraction of the mass of atomic nuclei. What fills the gap is energy stored in motion and in the gluon field itself. When quarks are confined, they cannot remain still. Confinement forces them into constant interaction. Gluons are exchanged without pause. The field between quarks carries tension. That tension represents energy. According to the relation between mass and energy, that stored energy contributes directly to the measured mass of the particle. In this sense, mass becomes less about substance and more about structure. A proton weighs what it does, not because it contains heavy building blocks, but because it contains a tightly organized field configuration. Gluons sustain that configuration. They generate the forces that prevent quarks from dispersing, and in doing so, they create the bulk of the proton's inertia. This understanding extends outward. Atomic nuclei are assemblies of protons and neutrons. Their stability depends on residual effects of the strong interaction between these composite particles. That residual force is itself a consequence of the deeper gluon field operating inside each nucleon. The chemistry of atoms depends on nuclei, the structure of matter depends on atoms, and the mass of nuclei depends predominantly on gluon dynamics. The influence of gluons therefore reaches far beyond the tiny scale at which they operate directly. Their presence is encoded in the solidity of tables, in the density of planets, and in the gravitational pull of stars. All of this rests on the confined, self-interacting field that binds quarks together. The reach of gluon dynamics into everyday matter might suggest that the strong force operates over long distances in the same way gravity does. Yet, this is not the case. Outside a proton or neutron, the strong interaction falls off rapidly. Atomic nuclei are bound together, but the force that holds separate nuclei at a distance is negligible. This short-range behavior follows directly from color neutrality. A proton is internally full of color charge, but externally it presents no net color. The gluon fields of its constituent quarks combine in such a way that their effects largely cancel beyond the proton's boundary. What remains between neighboring protons and neutrons is a residual interaction, sometimes described as a leftover trace of the deeper strong force. This residual force is strong enough to bind nuclei, but it does not extend indefinitely. It decreases sharply beyond the scale of the nucleus. The fundamental gluon field remains confined within color-neutral particles. This feature distinguishes the strong interaction from electromagnetism in a precise way. Electric charge can exist in isolation, and its field extends outward without limit. Color charge cannot exist alone under ordinary conditions. Its field is trapped inside composite structures. The short range of nuclear forces is therefore not a limitation of gluons. It is a consequence of their effectiveness. They confine color so completely that large-scale color fields do not persist. This confinement also protects the larger world from the full intensity of the strong interaction. If color were not confined, matter would behave very differently. Interactions between particles would be dramatically stronger at all scales. The structured complexity of atoms and molecules would not emerge in the same way. Instead, the strong force operates intensely but locally. It governs the internal architecture of hadrons and the cohesion of nuclei, while allowing electromagnetic and gravitational interactions to dominate at larger distances. In this layered arrangement of forces, gluons occupy the deepest level of visible matter, shaping its core while remaining hidden from direct observation. Because gluons confine color so effectively, they also define which combinations of quarks are allowed to exist as stable particles. The simplest combinations are baryons, which contain 3 quarks, and mesons, which contain a quark and an antiquark. In both cases, the total color charge cancels. These structures emerge naturally from the rules of color symmetry, but the theory itself does not forbid more complex color-neutral arrangements. It allows, in principle, combinations such as 4 quarks and an antiquark, or 2 quarks paired with 2 antiquarks, provided the total color balances. Over the past decades, experiments have identified candidates for such exotic states. These particles are short-lived, yet their existence supports the underlying framework of gluon-mediated binding. What remains consistent across all these cases is the requirement of color neutrality. Gluons enforce that rule without exception. Inside these composite particles, the gluon field arranges itself differently, depending on the number and configuration of quarks present. The pattern of confinement adapts, but the governing principle does not change. Color must cancel overall, and gluons provide the mechanism for that cancellation. This adaptability highlights an important feature of the strong interaction. It is not limited to one rigid structure. It supports a spectrum of bound states, each corresponding to a different internal arrangement of quarks and gluons. The diversity of observed hadrons reflects the richness of the gluon field. Yet even with this diversity, the number of stable, long-lived particles remains small. Most possible combinations decay quickly into lighter, more stable forms. The strong interaction determines not only what can bind, but also how those bindings transform. Through this ongoing reshaping, gluons govern the internal taxonomy of hadronic matter, defining which structures persist and which dissolve. The ability of gluons to sustain many possible bound states raises a deeper question about limits. Is quantum chromodynamics a complete description of the strong interaction at all energies, or does it eventually give way to something more fundamental? Within the range of energies we can probe directly, the theory has held firm. High-energy collisions test its short-distance behavior. Lattice calculations test its low-energy regime. Observations of Quark-gluon plasma test its collective properties under extreme conditions. In each case, the predictions derived from gluon dynamics align with measurement. Yet there are regimes that remain beyond direct experimental reach. At densities far greater than those produced in laboratories, such as those believed to exist in the cores of neutron stars, matter may enter unfamiliar phases. In such environments, quarks could form new collective patterns, possibly pairing in ways that resemble superconductivity. Gluons would still mediate the interaction, but the overall arrangement of the field could shift into configurations not yet fully understood. Even here, however, the governing equations remain the same. What changes is the state of the system, not the underlying structure. Another open challenge concerns the precise mathematical proof of confinement. Numerical simulations demonstrate confinement convincingly. Experimental evidence supports it consistently, yet a simple analytic derivation from first principles remains elusive. The behavior is established, but its most elegant proof has not been written. This boundary does not signal instability in the theory. It marks a region where calculation is difficult, not where evidence is lacking. Quantum chromodynamics continues to function as a coherent framework across scales. Gluons remain its central actors, enforcing color neutrality, generating mass, and shaping the internal architecture of hadrons. The unanswered questions lie at the edges of extreme conditions and mathematical formality, not at the core of what has already been observed. While the mathematical proof of confinement remains incomplete in a formal sense, the physical picture has grown steadily clearer. The strong interaction is described by a theory with remarkably few adjustable elements. Once the symmetry structure and the existence of quarks are specified, nearly everything else follows. The number of gluons is fixed. Their self-interaction is fixed. The way the force changes with distance is fixed. Only a small set of parameters, such as the overall strength scale and the quark masses, must be determined experimentally. This economy gives the theory unusual rigidity. It cannot be easily reshaped to fit data in arbitrary ways. When predictions succeed, they do so because the structure is internally constrained. One of the most striking aspects of this structure is how it balances simplicity and complexity. The governing rule is compact, color symmetry enforced locally across space and time. From that rule emerges confinement, asymptotic freedom, jet formation, hadron spectra, and the bulk of visible mass. The same equations describe the behavior of quarks at distances far smaller than a proton and at temperatures comparable to those of the early universe. Across this enormous range of scales, gluons remain the carriers of interaction. At extremely high energies, well beyond those currently accessible, it is possible that the strong interaction may unify with other forces in a deeper framework. Some speculative theories explore this possibility. Yet within the energies directly tested, quantum chromodynamics stands as a complete and self-consistent description. The gluon does not appear as a free particle in ordinary space. It leaves no isolated track in a detector, and yet its presence is written into every proton and neutron. Its influence shapes the mass, stability, and diversity of hadronic matter. What began as a necessity to explain nuclear binding has become a central pillar of modern particle physics. Because quantum chromodynamics is so tightly constrained, it leaves little room for ambiguity in how gluons behave. The strength of the interaction at short distances has been measured with increasing precision in collider experiments. As particles are accelerated to higher energies, the effective coupling between quarks decreases in exactly the way the theory predicts. This gradual weakening has been mapped across a wide range of scales, and the results align with the equations derived from color symmetry. At intermediate energies, where quarks are confined but still probed indirectly, the patterns of hadron production continue to follow the expectations set by gluon dynamics. The relative frequencies of different particle types, the angular distributions in jet events, and the subtle correlations among produced particles all carry the imprint of gluon exchange. These signatures are not isolated curiosities. They form a consistent network of evidence reinforcing the same underlying structure. At low energies, where direct analytic calculation becomes difficult, lattice simulations provide an independent route. By discretizing space-time and computing the behavior of quark and gluon fields numerically, physicists have reproduced the observed masses of many hadrons with increasing accuracy. The proton, neutron, and a wide range of mesons emerge naturally from these calculations. The fact that these results arise from the same fundamental equations that describe high-energy scattering gives the theory unusual coherence. There remain frontiers where knowledge is still being refined. The internal distribution of gluons inside the proton at extremely small fractions of momentum is an area of active investigation. New experiments aim to map this region with greater clarity, examining how densely gluons can accumulate and how their collective behavior evolves. These studies do not challenge the existence of gluons. Instead, they explore the detailed texture of a field whose presence is already established. In astrophysical settings, the role of gluons may influence the structure of neutron stars, where matter is compressed to densities far beyond those found in atomic nuclei. The precise arrangement of quarks and gluons under such conditions is still being modeled, yet even here, the governing equations remain those of quantum chromodynamics. The uncertainty lies in the complexity of solutions, not in the identity of the force carrier. Across laboratories and across the cosmos, the same gluon field governs the behavior of strongly interacting matter. Its effects are measurable, its structure constrained, and its predictions repeatedly confirmed. The remaining open questions lie in extreme regimes and in mathematical elegance, not in the foundation of the theory itself. When we gather these threads together, a coherent picture comes into view. Gluons are massless carriers of the strong interaction, emerging from a local symmetry associated with three types of color charge. They differ from photons because they themselves carry the charge they mediate. This single feature gives rise to self-interaction, and from self-interaction flow the defining behaviors of the strong force. At very short distances, gluon self-interaction causes the effective coupling between quarks to decrease, allowing quarks to behave almost freely when compressed together. At larger separations, the same self-interaction reorganizes the field into concentrated flux tubes, leading to confinement. Quarks and gluons remain permanently bound within color-neutral combinations under ordinary conditions. Within protons and neutrons, gluons are not passive messengers. They carry a significant fraction of the internal momentum. Their dynamic exchanges generate most of the mass of visible matter through confined energy. The weight of everyday objects arises largely from this structured activity at scales far smaller than atoms. Even the vacuum of the strong interaction is shaped by gluon dynamics. Fluctuations and field configurations influence how quarks move, and how confinement persists. Under extreme temperature or density, confinement can relax into new collective phases, such as quark-gluon plasma, yet the same underlying field continues to operate. The theory describing all of this, quantum chromodynamics, is compact in its assumptions and broad in its reach. It connects jet patterns in particle detectors, the stability of atomic nuclei, the mass of the proton, and the early moments of the universe within a single framework. There are edges to current understanding. A fully rigorous analytic proof of confinement remains to be completed. The detailed behavior of gluon fields at the highest densities is still being explored. Yet within the vast range of tested conditions, the structure is stable and consistent. Gluons do not appear in isolation. They cannot be held or observed directly as free particles, and yet they are indispensable. They bind quarks into protons and neutrons. They generate the mass that anchors matter. They define which combinations of quarks can exist. Through their self-interacting field, they shape the deepest layer of ordinary substance. At the core of every atom, within every nucleus, quarks exchange gluons in a continuous, governed pattern. From that pattern arises stability. From stability arises structure. And from structure emerges the material universe we inhabit. Seen from a wide enough perspective, gluons represent a particular kind of explanation in physics. They are not introduced to decorate a theory or to multiply unseen entities. They arise because the stability of matter demands them. Nuclei remain intact despite electric repulsion. Protons and neutrons possess internal structure. Quarks behave almost freely at very short distances, yet never appear alone. The mass of visible matter far exceeds the sum of the intrinsic masses of its quarks. Each of these observations points toward the same underlying mechanism. A self-interacting field associated with color charge binds quarks together. Gluons are the quanta of that field. They do not travel freely across the universe under normal conditions. They are confined within hadrons, shaping their internal dynamics, yet their influence extends outward indirectly through the stability of nuclei and the mass of atoms. Every solid object owes its persistence to the energy stored in gluon fields. Every star relies on nuclei whose cohesion depends on the deeper binding of quarks. At extreme temperatures, the boundaries enforced by confinement can soften, revealing a phase in which quarks and gluons move collectively. In the early universe, this state filled all space. As cooling occurred, confinement reasserted itself, and the building blocks of ordinary matter emerged. The transition was governed not by chance, but by the same structure that still operates today inside every proton. There remain mathematical challenges and extreme regimes yet to be explored. But within the conditions we can test directly, the role of gluons is firmly established. Their properties are constrained by symmetry. Their effects are measured in experiments. Their consequences are visible in the mass and stability of the world. Deep within the nucleus, beyond direct sight, quarks exchange gluons in a continuous and orderly pattern. That pattern does not waver. It sustains the structure of matter from the smallest scales outward, and in that steady exchange, the strong force quietly holds the universe together.